Well, I have here a list of the people the school thinks are in the class. I need your initials. If you've already signed it Friday, never mind, but if you have not, then come around after class and initial opposite your name so you'll be in class. Because if you don't initial it, then they will think you're not in the course. And you'll have to argue with them about it. Today I'm taking up information theory. This was created by Claude Elwood Shannon in the 40s. He was working for a telephone company, and we were concerned with how much information are we sending where, what are we doing, what is the nature of the business. And he came up with information theory. Management and some of his friends suggested he should have called it communication theory. But he chose information theory because it sounds so much nicer. And so people this day think it deals with information. Well, yes and no. As one of the purposes of this lecture is to tell you to what extent it's yes and what extent it is no. It's a touchy subject. Well, what is information? Shannon identified it with surprise. If something very surprising happens, you've learned a lot. If something less surprising happens, you've learned less. And if a certain event happens, then you've learned nothing. You knew it was going to happen. So it turns out roughly, and I will derive a formula in a few minutes, that the log of the reciprocal of the probability is the amount of information. If certainty is 1, the log of 1 is 0. A half, the reciprocal of a half is 2, the log of 2 is the amount of information. Now, you normally took logs in base 10 or base E. In this course, in any course in information theory, you generally take logs to base 2. Every log system is proportional to every other one. There's a fixed constant which multiplies logs of one variable into the other. So there's no real difference. The advantage of base 2 is that then for one binary choice has one binary digit of information or abbreviated bit. One bit of information is contained in one binary choice, provided both sides are equally likely. Now, let me make a partial derivation. Shannon said, you know, the amount of information in two independent events, P1 and P2, the roll of die and the cost of a coin. The amount of information should be, for independent events, the sum of the amount of information. The amount of information I got from the die plus the amount of information I got from the coin. That's what should be true of information for independent events. Well, if I put P1 equal to P2 equal to P, I get I of P squared equals 2I of P. If I put this equal P squared, that one's P, I get I of P cubed is 3, and in general I will get I of P to the nth is N I of P, which says if I toss a coin N times, I get N times as much information I get from one toss. Seems reasonable, doesn't it? Well, now, using exactly the method you used when you took algebra, you extended exponents from integers to fractions, it's straightforward to obtain I of P to the the M over N is M over N I of P. Straightforward. Now, Shannon assumed that the amount of information I is a continuous function of P, the probability, which seems reasonable. If so, then this is true for all values. Since it's true for all the rationals, it's true for all values if the function is continuous. And from this you deduce I of P is log P proportional to it. And we will find out, we'll fiddling a moment, it's minus log P to the base 2 or log 1 over P to the base 2. It comes out straightforward. You can show the uniqueness of it, such other things without any trouble. It's the standard Cauchy difference equation. So This is why we think the logarithm is measures the amount of information. The bigger the surprise, the smaller p is, the more. Now you say, well, probability of zero events got infinite information. Yes, but it never happens. So we now want to know, given an alphabet of symbols, S1, S2, Sn, with probability P1 and P2 up to Pn, how much information is in this distribution on the average? Well, it's easy. The probability of seeing the symbol times the amount of information I get from that symbol will be the amount of information on the average. I running from over the whole alphabet 1 to Q. This is the amount of information. This is the probability I see that amount of information. That's the quantity. Now that's called the entropy. The entropy is the expression that arose in statistical mechanics and other places. It has the same algebraic form. That two things have the same algebraic form does not mean that the variables have the same meaning. You can have two quadratic equations. The variables may have very different meaning, likewise the coefficients. The story goes, which I've never verified, although I knew Shannon fairly well, I never bothered to verify it. This Shannon talking with von Neumann. Von Neumann said, look, it's the same expression occurs there. Nobody understands entropy anyhow. Why don't you call it entropy? Because if you do, you'll always win in any argument. So Shannon did. But it's dangerous to suppose that that entropy is connected with the entropy you learned in physics. What connection it is, some people believe it's exactly the same. Some people thought it's exactly the opposite. It's negentropy. Its knowledge is the opposite of disorganization. So they want to call it negentropy. Well, it's a convenient thing for entropy. It's a convenient expression which occurs, as you'll see, all the time. And so I need to do something about it. Now the first thing I need to do is get our boy Gibbs inequality. Given a distribution Pi and another distribution Qi, two different probability distributions, I'm going to look at the summation Pi log Qi over Pi. I running from 1 to Q, of course. Now I'm going to use an inequality. The log function of base e has a slope 1. And this line is x minus 1. So I assert the log of x, the base e, is less than equal to x minus 1, and it's equal at the point x equals 0. Whoops. Yeah, x equal 1, sorry. This at x equal 1, they're equal, the log quantity. So I will replace it here. I get Pi, x is Qi over Pi minus 1, and that's nothing else than summation Pi minus summation Qi, or sorry, Qi minus Pi. But that's 1 minus 1, which is 0. Therefore, this thing is, and the equality will happen only when the q's are equal to p's. Now, if I take the q's, all 1 over q, I deduce almost immediately that Pi log 1 over Pi is less than equal to log q. The entropy is bounded above by that. The log of the number of symbols bounds the entropy above. And if all the q's are equal to p's, all the q's are equal to p's, then these are 1s. That thing exactly holds. So you have the maximum entropy when all the probabilities are the same. That's the maximum certainty. The maximum uncertainty arises when all the p's are equally likely. If you have a perfectly balanced die, you don't know what's going to happen. If you've got a loaded die, you are getting less information because you have an idea what's likely to happen. So this agrees with what you tend to think. The maximum entropy occurs when all the probabilities are the same. It's a big, big help on that one. Now I'm going to take the Kraft inequality. You remember that one? This was less than or equal to 1. Well, I'm going to consider some QIs, which are going to be 1 over 2 to the Li divided by K. Now you see the sum of the QIs is equal to 1. I fixed it up that way. If I use those Q's in here, what I will find from some simple algebra will be, and I want to get the thing in the form I want it in, the entropy H of P, that entropy right there, is less than or equal to L, the average code length. You give me the entropy of the probabilities, I can give you the minimum distance, the minimum average code length, the thing we wanted. Entropy gives a lower bound. You can't do better than that, provided the translation is one symbol to one symbol. It gives you a nice lower bound, so it's connected with things. It shows you the nature of the problem. It tells you this entropy does play a role in coding theory. It tells you the maximum entropy occurs when all the p's are equal, and the entropy is a lower bound on the average code length. So we have some advantages. We know more or less where we are going to be. And this is what is called the noiseless coding theorem of Shannon. This is the best you can do without any presence of noise. Now you remember I drew a picture, a source encoding a channel, and so on. The channel had noise. If there is noise, how well can I do? And this is what Shannon set out to try and prove his noisy theorem. Now it's a very difficult theorem to prove, but I'm going to give you a cut down version for the binary symmetric channel, meaning just two symbols plus 0 and 1 and equally likely. The binary symmetric channel can be looked at this: 0, 1, 0, 1. The probability of 0 going to 0 is that. The probability of 0 going to 1 minus p. Being symmetric, this is p and this is 1 minus p. That's the kind of a channel you want to think about, because if you don't have that channel and you're throwing more zeros going into ones than ones go into zeros, the repairman will adjust the voltages and other things so you roughly have that kind of a channel. A 0 is as likely to go to a 1 as a 1 is to go to a 0. Therefore, the entropy of P is P log 1 over P plus the other symbol, Q log 1 over Q, and that's H of Q. Now I have this channel in general. I'm going to send a whole string of them. I'm going to send the nth extension. I'm going to send a string of n ones and zeros to you. You're on the receiving end. It's now what I send you, you're not going to get. Some of the digits will be distorted by noise, because we're now looking at a noisy channel. Well, I've got the nth extension, and n will be determined later. We will keep saying if I take a big enough n, I can do this. If I got a big enough n, I got that. Well, all through, when I finally take the biggest n I have to have, that will determine n. Now there'll be m messages. M is also ultimately going to be determined by the inequalities you want. Furthermore, I'm going to make the assumption, which is an obvious one to make for ease, the probability of any message, any one of the messages, is 1 over m. They're all equally likely. All strings are equally likely in this nice symmetric channel. Well, that gets us along a little way. And now we got to look at channel capacity, which I don't want to get involved with terribly. But the channel capacity will be derived to be C is 1 minus H of P. Remember, if all the P's are equal, H is 0 and channel capacity is 1, you can get 1 bit through. If, however, the P's are not, there's some probabilities of, see, the probability of 1 is 0, and the probability of 0 entering into the P log P will produce a 0. So the uniform one, or the alternate one which has a 1 at one place and 0 every other one, works out. But if I don't, then the channel capacity is downward, and the channel capacity was defined to be the maximum you get through that channel for any encoding, which means, by definition, you can't do better. This is the most you can get through the channel by any encoding system, get through reliably, of course, that you know what is getting through there. So that channel capacity is being defined. Now, I can't achieve channel capacity, so I'm going to have to go channel capacity 1 minus epsilon. I'm going to have to go a little less than channel capacity. You pick as small as you want. Let E1 be as small as you please. How close do you want channel capacity? You pick it. Now, if I send, that's per bit. If I send n bits, that's the amount of information I get through. And so that's not bad. Now let's see what we do next. Yes, now the number of messages is going to be 2 to the n If I'm going to have that capacity, I've got to have this much. They're all going to be equal, like you said, the probabilities will be reciprocals. So I have that much done. Next is I've decided what it is in terms of the E1 that I have. Now, let me look at it from my position. There is the letter I'm sending you. Here is a sphere. That sphere is a radius nq, where q is the probability of an error, n is the number of bits sent, so that's the expected number of errors, right? Right? Now, I may make more. In fact, what I'm going to do is increase this sphere, so the radius is nq plus e2. It's going to be a little larger. Now let's stop and think for a long while about what happens in the central limit theorem when I toss a coin many, many times. If I toss a coin 10 times, I expect 5, but I wouldn't be surprised if 6 or 4 or even 7 or 3, but I would be surprised at 9 heads, right? Now if I toss 1,000,000, now, I would be surprised, very surprised, if I got 600,000. Percentage-wise, when it's very small, I expect big variations. When it is large, I expect small variation. But I would be very surprised if I got 500,000 plus 1 or 500,000 minus 1. I expect to be roughly the square of the number of tries. This is what the central limit theorem says. The variability is typically equal to the square root of the number of tries. So I expect to get something like this. Now remember the other day I carefully introduced you to a function where the ratio approached 1 but the difference got to infinity? I'm looking now at ratios. The ratio is going to behave itself because I dealt with this ratio percentage-wise. The q was n was increased by that amount. Well, as a result, if you look at what happens along this radius, what's the probability of error? You see it peaks up and comes down. But of course, there's a little bit outside. The bigger n is, the more peaked this is about the expected value, which is the radius, nq. The less there'll be out there. You tell me how much you're willing to tolerate out there. How much? And I will pick an n so large that the probability of error will be very small. Now I need to look more at the probability of an error. I also have to look at the thing from your point of view. Besides, you see, I sent a message, letter SI, or what the heck, let's use the notation I used, AI. I send some simple AI, and you receive a BJ. That BJ may be inside the sphere, it may be in this outer sphere, it may be outside. Any one of the things. This is moved from A to some B. Now, from your point of view, you received a BJ. If the BJ were inside my sphere, the AI is inside your sphere. If the BJ is outside the sphere, the AJ is outside, right? This is how you see it. This is how I see it. I see it this way. You see it that way. You've got a B and you wonder what A did Hamming send. Well, what's the probability of an error? It could be that I send an AI and AI in, yes, another. There might be another AI inside the sphere. There might be several AIs, in which case you don't know which one I sent. It might be that yes, I'm in, and no, there's no other AI. It might be that it is not in, and there is another AI, and it might be no, no. That's the only one of the four cases which you can do anything with. If any other three cases arise, you don't know what to do. You have no way of knowing. So what's the probability of an error? It will be the sum of those three. The probability of an error will be another AI. See, let's get these two first. The probability AI is not in SR, where SR is the radius of this sphere. If it's not in there, you're dead. You're going to get the wrong answer. Plus, the probability that AI is in the sphere times the probability no other. Well, this one. I claimed I could make the n so large that this amount could be made as small as you please. I'll call it the amount d. By picking n sufficiently large, the probability that the AI I set is not in the sphere, is out in that little tail, you can make it as small as you want. Here I have plus these. Now this thing I'm going to call 1, the number 1. So I have summation of all the p such as AI is in the sphere and no other. Now I've got to make a break and say, how will we make a code book? How will I make this code book of M symbols? Well, remember Shannon's doing this very early in the 40s. I haven't invented error correcting codes yet. He doesn't know anything about that. He doesn't know much. So he says, well, I'll toss a coin. If I have to have n bits, I'll toss the coin n times, and that will be the first symbol. The second symbol. So there will be n m tosses. And I will get the code book. Now you'll say, There's a danger that two of those will be the same, and the answer is yes, there is. I must show that danger can be held down. Now, how many code books are there? There are 2 to the nm code books. If you put it in any order. That's the number of times you toss a coin. They give you all plus minus ones. That's the total number of code books. Well, n is going to be large. M is n to some power. That is a very big number. The code book itself, for a reasonably small error and close to channel capacity, printed on normal paper, would fill the solar system. Nevertheless, we're talking theory. We're talking theory. Can it be done? Not, is it practical? Because I got to talk both sides. It is theory I've talked about. Well, now, if I made the code book this way, where all the code books were obtained by random tossing, then I'm going to do something. The probability of an AI of, say, probability 1 or more in there will be less than or equal to the sum of the probability of any one. Because if there were several inside, you'd be wrong. I'm going to count every time there is one inside wrong, so I'm strengthening it. But this, because the way the code books are mentioned, you pick any other j, and when I come now, as I'm going to do to average over all code books, I'm going to calculate the average p error. Well, the average of a constant is a constant. Well, what happens? These points go through all the space except AI. The AI is sent. It goes through every other value, every one of the positions in the code book. This symbol, sooner or later, takes on every possible value. That one takes on every possible value. That one takes on, because I went through all possible code books. So I have m minus 1 times the probability of another A inside. That's where you're going to be in trouble. I got to show this can be brought down to small. If I show this is down small, I'm in. Well, what's the probability of another AI? How big is the sphere? Where S is some number bigger than Q plus E2, and such that S plus N is an integer and S is less than a half. So I'm looking at the sum of the binomial coefficients up to not quite the midpoint. Q had to be less than a half. I could not have had a signaling system. Well, put it this way. If I had a signaling system which the probability of error was bigger than a half, all I got to do is change the symbol for the opposite. I got a probability system less than a half, right? Right? So Q is less than a half. Therefore, I can do this. Now, this sum was gaily written down to be less than or equal to 2 to the n h of S, we'll say. H of S or lambda. What letter do I want to use? H of S. Well, I read about it referring to something else. I look at the darn inequality, wonder where it comes from. I try looking several places and I can't find it. Everybody always refers to a well-known sum. I've looked at several. I finally found one of the derivation, but the derivation is so messy that me being kind of stupid, I can't read it. It's too complicated. So I do what I normally do, and I advise you to do it. Sit down and say, well, how can I calculate this sum? All right, this is the biggest. The biggest one is the last binomial coefficient in the distribution. Remember, it's over there. So I use Stirling to get an approximation, a nice, neat one. And now I look at the ratio of this to this. and use that rate all the way down, which this being the biggest. Let's see, one. This is going to be overestimated. I'm going to, if I take that ratio and apply it all the way down the line, these will be larger. Now if I go out to minus infinity, I have a geometric progression which I can sum. So I sum it. I come up with something like s to the s, 1 minus s to the 1 minus s. I look at that thing. Now I knew there was an entropy. I realize if I take the log, I get s log s plus 1 minus s log 1 minus s. And you see there's my entropy. So that's how this inequality arises. And you see, again, this entropy function is remarkable. Binomial identities, the entropy function arises. It arose all over the place. Well, now if I take that and various other things and plug them all in there, I can show that this is arbitrarily small by sufficiently large n. So I have the average error, if I make n sufficiently large, with this kind of a simple coding system, simple hypothesis, I'm arbitrarily close to channel capacity and I'm arbitrarily accurate, provided I pick things certain ways. And the book gives you some more details, and I don't want to waste your time on them. Now you say, how come? Well, let's back up. Remember that lecture on n dimensions? All the value of the sphere was right in the surface. The errors were all right there. There wasn't anything inside. They were all right there in the surface. If I make a small shell about it, man, I've got all the errors. Next, you remember if I got a bunch of spheres, how can I prove these spheres don't overlap? So these spheres we drew for each message point, the spheres are not overlapping. Well, you remember how vast n dimension was and how many orthogonal directions there were? Remember those? Well, that's why. I can put these spheres in, pack them in there with arbitrary small chance of overlap, and pack in as close to channel capacity as you want, provided you let me raise the dimension n as high as I want. Now Shannon argues further now. He says, if the average is arbitrarily good, there must be at least one good one. Everybody can't be worse than average. So he says, that shows you there is an arbitrarily good code, arbitrarily close to channel capacity, arbitrarily accurate. Now, much of the proof was semi-constructive, except that I told you the numbers were kind of big. But at the back end, it isn't constructive. Well, Shannon wanted to try and make a random code book one time. And at that time, I was in charge of the computing people, which consists of a bunch of girls typically with desk calculators. And so we designed a computation with as many symbols as there are lines on a typical ruled sheet of paper. And we tried picking random numbers and calculating how good a code would be. Well, several, maybe a dozen tries or more, and none of them were any good. So I said, well, maybe what we should do is look at the codes when we try to put in which point is blocking the trouble. And maybe some points are badly positioned so nobody can get in. Let's remove those and see if we can't get a little further. And we tried various artificial intelligence devices. By throwing out previous choices now and then and putting other ones in and so on, we never came near anything. That n has to be very, very, very large. Now, what does that mean? If you're the signaling officer, a message comes to you, you have to have a very long message before you encode it. If he merely wants to send out SOS, you got to wait and you got another billion letters, then you can encode it and ship it efficiently. You can't ship a short message efficiently. So you can see why we don't really want quite what Shannon did. On the other hand, Shannon does tell you, if you want to be efficient, you have got to have a large code because I've got to have that thing apply. If I build a system which will correct 10 errors and almost all the time is only correcting 5, I'm wasting capacity, right? I must be very close to correcting the maximum number I can. And that's why you find in communicating from the satellites back to Earth, you have maybe 5 watts or less. If there's solar cells way out there, the sun isn't very bright, and if it's a nuclear energy power source, it's been running for some years and it's got too good. As a matter of fact, we've got some out there in space now, well away from the solar system. The solar system, remember, is a sort of a flat pancake. We sent them out and we hooked them, one down and one up. And they are now very far away, sending back to Earth. They've got little dishes. We've got 200-foot dish. They got 5 watts, best, probably 3 watts. And you're supposed to be reading it on Earth? Yes, we are. Because these codes correct up to 100 or more errors per block. They send you a huge N block and they correct up to 100 errors in the block. They had to resort to very, very good codes because there was no way to beat down the noise. I could not have the power out there. And I haven't got the dish out there. And I haven't got the dishes on Earth more than a couple hundred feet. The thing is just broadcasting more or less towards Earth, but it's covering the whole Earth and more because it can't focus with that small radio. A antenna cannot focus it that sharply to hit one spot on Earth. Besides, it's got to hit a bunch of spots. It's got to hit the back side and the front side depending on where it is. When we roll tide to the back side, we have somebody else off in Australia reading it and so on. So we do this. We know that from Shannon's theorem that we will have to have very great accuracy, meaning very great encoding lengths. Now, the code books being random, there can be no compression. Hamming codes were regular. They used computing. You don't construct the code book. You calculate what the correct answer was. You don't look it up in a book. It's quite a different thing. And these likewise. Those are calculating methods. They are not random codes. They are very carefully calculated ones, correcting that up to 100 errors or more in a single block. It can be done. This is what you have to do in a jamming situation. When the opposition is trying to jam you, he's got more power locally than you got. And he's only got to knock out a few bits here and there and you're in trouble. So you have a very great problem. We have various devices which you must know of. Among others, high complex encoding. Another is shifting the frequency constantly in a strange way so he's never can only hit the frequency you're using now and then. So he knocks out a bit here, a bit there, a bit there, but he doesn't know what frequency you're going to use. You shift regularly, the receiver knows how to shift, and you get the message through that way. There are a lot of methods we've devised to get through noise. When nature produced the noise in space, the billions of miles, we did one thing. When you have an active enemy, you do something else. Now, nature is, by and large, as Einstein said, she's not malicious, but she can be difficult. So what you do when you're opposing nature is typical of this. When you are trying to oppose human beings, you've got to use some other difficult tricks to do it. But fundamentally, this is how we have done the problem. Now, I want to summarize this business, and I've got a little bit of time left. What you see here is a good example. I made a definition, or Shannon did, about information being surprise. It sounded good. It fits machines. It fits radio, television, the telephone company, computers. It fits very well. It doesn't fit humans. If you look at a random number, oh, by the way, another fault is it's relative. If you're looking at a random number source and every number comes as a surprise to you, it's got a lot of information. But if I tell you the random number generator, then you're able to predict the next number and you're learning nothing. Thus, whether you're learning something or not depends upon your state of knowledge. There is no how much information is in that signal. It's a combination of what's there and what you know. If you know a lot, there's nothing in the stream of random numbers because you know how they're generated. If you don't, then you're learning a lot. Secondly, as anyone who teaches knows, the students look baffled for a very long time, and then sometimes you say something and they all see it. Suddenly a few words and a tremendous amount of information comes into their heads. Something precipitates the confusion. But what you say doesn't always work. Some students see it and some don't. And if somebody says, what did you say? You generally repeat it in different words. Because you figure the first words weren't quite right because the understanding of the other person. So information practically from your point of view and mine depends upon the individual, depends upon other things, and we have with information the concept of meaning, understanding, insight, and so on. Shannon chose surprise. Now in every system, when you lay down a definition, you partly distort your original ideas. Therefore, when definitions are made, you should look carefully at the distortion. And when you finish it, go back and ask yourself how much did that definition make the consequences which we deduce be true. Short, how much follows from the arbitrary definition, and how much does it really fit my original idea of information. Now, an example of that business is the IQ. It's a perfect illustration of deception practiced at all levels. What was done originally is Binet picked a bunch of plausible questions which seemed to involve intelligence. He gave them to a bunch of people, found those which seemed to correlate and those seemed not to correlate. He threw out the ones which seemed non-indicative, and he finally made up an IQ exam. Now he scores it. And if I write the cumulative scores, I get something like that. But if I draw it on probability paper so that the probabilities are spaced probability-wise this way, and I read off the crossings, what do I find? I find that IQ is normally distributed because I calibrated the grading system to do this. Now you all know, if I know my class, I can ask some easy questions, some reasonably hard ones, and some very hard ones, and I'll get a distribution like that. If I asked an exam which all the questions were equally likely, equally difficult, I'd get a distribution like that. The students either know nothing or know everything. It's evident the exam can get any distribution you want. Is IQ normally distributed in the populace? That definition and the way they've done it, yes. Does it fit what you mean by intelligence? Not too well. Not too well at all. We find that frequently people who don't have really high IQs turn out to be very smart and very effective people. And we find frequently the brightest people in your college class didn't always do so well. Some of the dummies did a lot better. So evidently there's a simple example of where the definition, namely the ability to answer these questions, plus the method of scoring produces what you're always told. IQs are normally distributed in the populace. A, is it intelligence? And B, hell, you made it normally distributed. Always this kind of thing has to be looked at. Shannon's definition of surprise produces a whole bunch of theorems. Now, insofar as in coding theorem and we're doing codes and so on, we're using inequalities here, there, and yon, you felt it was meaningful. It's when I shifted to human beings. Now, I'll give you an example of where you're in trouble. Take the genetic business when they think sexes are mating. There's going to be a mixture of the genes. Is that sheerly mechanical? If it is, you can apply information theory. If, however, something else is going on, shall we call kind of intelligence you have, then maybe you can't. So what we've had to do is this. We have had to try applying information theory in all kinds of fields to find out whether, when we make the application, that is mechanical or there are factors that are non-mechanical. The only way to find out is try. So we've tried applying information theory in many, many fields and found many interesting things and many interesting failures, where evidently something is more than sheer mechanical. I'll summarize by saying it fits very well for machines. It fits computer machines, the telephone company, radio, television, the bits, it does very, very well. We're doing now, for example, using this same kind of entropy and other arguments, we've compressed television pictures down enormously. Very, very enormously, because there really isn't that much information in it. Originally you thought every spot was independent, but they weren't. And by looking at correlation, probabilities, and other structure, we've greatly reduced things to save bandwidth, which is expensive. So it's a very valuable thing. Now I want to close with a story by Eddington, the famous astronomer from England. He's a bit of a kook, but that's beside the point. He said some men went fishing with a net in the sea. They fished, and they examined the fish they caught. They decided there was a minimum size fish in the sea. They never caught fish that's smaller than that. You go looking at the world with your mind, the way it's wired. What you can see is limited. You're in the same boat as those guys fishing. You go with an instrument, and the instrument limits what you can see. And that's going to be a theme frequently in this course. How much the tool you are using limits what you can see. And how much, perhaps, your mind, being wired the way it is, limits what you can think or what you can see. You know your eyes can only see one octave. Your ears can hear up to, well, probably 15K at best to anybody in this room, probably down to 12 or 10. You know these things. You can only smell a few smells. Dogs can smell lots of things you can't smell with beans. You know these things. But the idea that the mind is also limited is harder to take by. Yet it's clear. You put up some definitions, you build a theory. Yes, it fits that theory, but it is not quite what you meant. Whether information theory applies, for example, I say to mixing of sexes, when we imagine a sperm and the ova getting together, whether that is purely random and I can apply information theory, or whether there are other facts, we don't know. We only can find out by applying and seeing whether it checks out by experiment. So those who didn't sign up will please sign up, and I'll see you next meeting Thursday.
Oh, thank you. I was going to say, oh, well, I don't need the tip.
Well, we're beginning 4 lectures on digital filters. If you think the lectures are on the topic of digital filters, they're going to be pretty dull. If you think the 4 talks on digital filters are a device to hang a great many stories on, then it's a different thing. And that's what it really is. I can't tell you stories in detail about how people do research, except about myself. It isn't polite, and furthermore, I really cannot get data on other people, how Einstein did things. Most people don't really get down to the nitty-gritty of how things go. So I'm forced to do this, talk about myself, and you will find, I think, that I am trying to underline a couple of points. One is that if you will do a little extra work each time and get down to fundamentals and study things until you understand them, then Pasteur's remark, luck favors the prepared mind, will favor you. That's really what's going on. So let me start first with the history behind my involvement in digital filters. I had a vice president, W.O. Baker, who I had very much admired, but in all my years there I was never in his office, and I don't think he ever came to mine. We would meet in the hall, and we would talk briefly. One time when I met him, I said, Bill, when I came to Bell Labs in '46, we were going from relays to electronic central offices. And there were a large number of old relay people who would not learn to use oscilloscopes or anything else like that. They were moved over to a location I mentioned where, and I said, to you they were an economic loss because they had to be getting out of the way, and to me they were a social loss because they were very disgruntled and unhappy. Then I went on. During the war, Bell Labs had developed at our military location analog gun directors and plotting boards and everything else. There were a great many expert analog people. When we came into digital machines, I watched a large number of analog people unwilling to convert. And I said, this same thing happened. They have been pushed aside, walked around and evaded, and they're an economic loss to you and they're a social loss to me because some of my friends are not really happy. And I went on and said, you and I know, and this was back in the early 70s, the telephone company is going to go digital as fast as it can. If we do not now lay down books and other things so people can convert it when they're young, we will have even more people intellectually lost because of change and socially unhappy. Because when the world passes you by, you are not a happy person. Well, he looks me square in the eye and he says, yes, Hammy, you should, and walks off. Well, I don't like digital filters. I don't know anything about it. But as I walk back to my office, I say, do I wisely ignore my vice president's remark? And in any case, even if he hadn't said it, considering the arguments I gave, should I neglect the importance of this topic? Obviously, I should do something about it. So I went to my friend Jim Kaiser, who I knew moderately well at that time, and said, Jim, you are the world's expert practically on digital filters. You wrote your doctoral thesis on it and so on, and you've done all kinds of work. There comes a time in people's career when they should stop and summarize it, write a definitive book that gets it all down where people can find the whole thing instead of scattered in 25 different papers. And he allowed I was right. And I said, fine, why don't you write a book? He said, well,